Hello, good afternoon. Welcome back to CS560. So today actually we're gonna start a new topic, okay? It's about greedy algorithms. All right, I think we have finished the chapter for programming, right? Double check just in case. Yes. Yeah, we have covered all the problems in dynamic programming. And actually, this new chapter, this new type of algorithms is actually very closely related to dynamic programming. And basically, it is, I would say, an algorithm that is easier to understand than dynamic programming because it doesn't solve all the sub-problems, right? So when we introduced the rod cutting problem, for example, which we solved with dynamic programming, right? We first examined the problem by trying to find some property called optimal structure or optimal substructure, right? Which is another way to say that in order to solve the original problem, we need to find the optimal solutions to the sub-problems, right? Which is pretty similar to the presumptions for divide and conquer approach, right? So in the rod cutting example, we need to examine all cases, right? Given a rod, if it's 5 inches, then we have 4 different places to place our first cuts, okay? Then each of these 4 options will result in a left part and the right part, okay? So the optimal structure is that we need to solve the right part, the remainder parts, use the same algorithm, right? We want to know the optimal revenue for the right part, okay? So, and in order to obtain the optimal solution for the original problem, we need to explore all possible sub-problems. We need to solve all possible sub-problems. And that is a characteristic of dynamic programming approaches, right? We need to explore the sub-problem space exhaustively. We don't want to miss any possible sub-problems because our goal is to have the optimal solutions. That means we need to compare all possible solutions. Okay, so that's why dynamic programming requires some good top-down top-down design, like top-down overall design of an overall idea of how many possible sub-problems are there, okay? So, which makes it a difficult approach, or well, not that easy approach to understand, okay? So let's go back to the topic this week. The greedy algorithms is a type of algorithm that can basically solve problems in a similar way to dynamic programming. Like we need to get the optimal solution to some problem, okay? But the good news is that in the greedy algorithms, we don't actually need to exhaustively examine all possible solutions, okay? We will need to use some heuristics to choose to make the locally optimal solution, rather than making sure that our current local solution is the global best solution. Okay, so which saves us time to look at more subproblem space, to a bigger subproblem space. Okay, so it in terms of results, in terms of running time, the greedy algorithms is usually a pretty efficient algorithm compared to dynamic programming algorithm solutions. Okay, so I think it will be easier to understand it if we go through some concrete examples. And in this chapter, we will basically cover three concrete examples. The first one is called activity selection problem, and then we'll cover Huffman codes, and lastly, we will spend some time on a very classical example that connects greedy algorithms with dynamic programming. Okay, we will see how the same problem can actually be converted to a dynamic programming problem, and then how it is related to the greedy algorithms problems. Okay, all right, but still some theoretical discussion would be helpful at the beginning. So greedy algorithms, it's usually suitable for optimization problems, which means we need to go through a sequence of steps. Okay, and at each step we need to make a choice among several options. Okay, so generally speaking, the general principle of a greedy algorithm is that whenever we need to make a choice, we always make the choice that looks the best at the moment. Okay, by it looks the best, we mean that we just make some locally optimal choice. Okay, without the global information. Okay, we are not sure whether our current choice will actually lead to the globally optimal solution. Okay, of course, this is risky because sometimes the locally best choices is not necessarily the globally optimal one. Okay, so it depends. So whether the greedy algorithm can apply to certain problems actually depends on the nature of the problem. In some cases, the greedy algorithm is not sufficient to solve the problem, but sometimes it's just okay. Okay. And in those cases where greedy algorithms works, usually speaking, the same problem can also be solved by a dynamic programming. Okay, but in those cases, dynamic programming is just an overkill. Okay, we don't necessarily need to fully explore the subproblem space. All right, so as we said, we will look at three specific problems. So today we're going to cover activity selection problem, and then on Thursday we're going to cover Huffman codes and maybe with knapsack problem as well. Okay. All right, so let's look at this very practical problem. We actually come into this type of problems in our everyday life. Okay, so it's about scheduling. Okay, say we have some resource, we have a room space, right, which is vacant, and we want to like schedule activities, okay, using that room. Okay, and those activities actually compete with each other, right? We need to know that we need to make sure that there's no conflict between those activities being scheduled, right? Because they require exclusive use of the same room. Okay, so if I'm a manager of this room, right? So the goal for me is simply to select to schedule as many activities as possible, right? As long as they are mutually compatible, as long as the the first activity does not conflict with the second one. The second one does not conflict with the third one, right? So that I'm making the most out of this room, right? So this is a very typical optimization thought, right? We have some goal, we have some resource, and we want to optimize the outcome based on our selection. All right, let's further lay out some conditions. Say we use the notation A1 to AN to represent the activities being proposed, okay? And also, we also have the information of the start time and the finish time for these activities, right? So that makes sense, right? In order to, we have full information about the candidates' events, candidates' activities, okay? And so assume that the start time and finish time for each activity is listed in this table. We have 3 rows, right? The second row is the start time, right? Start time. We use SI to indicate start time and FI to indicate finish time. The I is just the index for the activity AI. Okay, so in this table we have first sorted all the activities. So it's in an increasing order by the finishing time. Okay, so of course we can also sort the activities by the starting time, but this will lead to a different kind of solution. All right, we will stick with this sorting by finishing time. Okay, so you see that's A1 finished by before 4 o'clock, A2 finished by before 5 o'clock, and A3 is before 6 o'clock. Okay. All right, let's further observe the activities. Okay. Then if AI, the activity AI is selected, then it takes place during time interval like between SI and FI, okay? So this interval here, actually on the right, on the left, it's a closed boundary, on the right, it's open boundary, but it doesn't really matter actually. So it's just to indicate the starting time and ending time. If we're gonna plot it on the scale, then it's gonna be a segment on the number on the scale, right? All right. So now let's consider whether 2 activities are compatible with each other, right? So we have AI and AJ, and we have the intervals. One is from SI to FI, and the other one is from SJ to FJ. So the whether 2 activities are compatible is also well defined, because as long as their intervals do not overlap, then we can say they are compatible, which means they can be scheduled within the same day, right? So as long as so there are actually 2 cases, right, in terms of the compatible. So like the example here, if the A1 and A2 are incompatible, which means they cannot be scheduled within the same day, then it's simply because if we look at A1 and A2, the intervals, right, have an overlap. A1 starts from 1 and ends at 4, but the A2 starts at 3, which is before 2 o'clock, right? So there's no way to schedule A2 while A1 is still going on, right? So unless the A1 and A4, like these 2 activities are very far away, like they never overlap. There's a blank here. So A4 can start from at 5 o'clock, which is after the time that A1 ends. Okay, so these are just the examples. So generally speaking, we can compare the starting time with the starting time of one activity with the end time, the finish time of the other activity. Say if the starting time, Si, is greater than or equal to Fj, which means I starts after J is finished, then apparently this case is a compatible case. Or in other case, if it's other way around, if J starts after I is finished, then that is also okay. Okay, so this greater than or equal to relationship, if we are describing the time, if describing one time is greater than or equal to the other time, then the greater one actually happens later. Okay, so that is our rule of defining the greater than or equal to relationship. Okay, all right. So in this particular example, let's say we just picked A3, A9, and A11, right? A3, A9, A11 here. So they are actually compatible, okay? But unfortunately, this is not the largest subset, which means we are not scheduling as many activities as possible, okay? And actually, if we look at A1, right? A1 starts at 1 and finish at 4, and A4, right? Start at 5 and at 7, and A8 start at 8 o'clock, and A11 start at 12 o'clock. See, so the starting time of A4 here is after the finish time of A1. And the starting time of A8 is also after A4 is finished. And the A11 starts after A8 is finished. So this is a perfect example of showing, okay, I can actually schedule four activities. And in this particular example, this 4 is the largest subset. Okay, well, there's another option, which is A2, A4, A9, A11. Okay, but as now we are like not considering, we're not maximizing the time. We're not maximizing the actual occupation time, right? The problem is a more simpler. It's like it's decided by the goal is like schedule as many number of activities as possible. It's not as longer time as possible. Okay, so it will be a different type of question if it's measured by the duration time. Okay, so again, how do we now we have the problem defined, then how do we get the solution, right? So actually, this problem can be it's pretty visualizable. Like if we plot the resource, which is the time we have for the room, then we can actually quite easily get to the point of how to solve the problem. Okay. So we just lay out all the activities. We just plot all the activities on this vertical, horizontal line of time, right? The horizontal line of time, which at the bottom of this plot is all the resources we available here. So this is the time, right? And we just plot each activities and let them stack onto each other, okay? So that it's very easy to observe whether we're gonna have an overlap in terms of occupation time, right? So let's start by asking the question, which activity we would like to choose first, okay? Because choosing an activity will have an outcome, right? After we have chosen this activity, then we are actually removing some time out of our pocket, out of our resource, right? Then only the time after this activity ends, or before this activity starts will be available for the other choices. Okay, so we need to consider this outcome of choosing an activity. Okay, so now let's consider this outcome by thinking about how much time do we have left after choosing some activity AI, right? Because that is pretty much the resource we have left after we choosing some activity, right? Say, let's assume that we select A1, right? So now we mark it as the gray color, then A1 is scheduled. Then because A1 finish at 4 o'clock, then if we look at the time scale, we only have 12 hours left that are available for other activities, right? Based on the principle of compatibility, right? That is very straightforward. We only have 4 o'clock to 6 o'clock available. Okay, so now our problem is changed. So now we are considering the remaining parts, not the original problem. We're considering the remaining part from 4 o'clock to 6 o'clock, 16 o'clock. So the problem becomes, which activity can we choose next among these available resources from 4 o'clock to 16 o'clock, right? Can we choose? So well, that is the outcome of choosing A1 to be the first activity, right? Okay, what if we choose a different one? What if we choose like A2 to be the first activity, right? Then from 5 o'clock to 6 o'clock, 16 o'clock, which will be 11 hours that are available to other activities, right? Then it makes sense to look at all the other activities, right? If we choose A3 to be the first, then we will have 16 minus 6, okay? Because A3 ends at 6, so we only have 10 hours left, right? So that's clearly show that we have different outcomes when we choose different activity as the first activity. Okay, so the whole choice has a constraint, which is that we choose the one as the first activity. Okay, so if we are choose the one as the last activity, then it'll be a different thing we need to consider. We need to consider like what's the available time before this activity starts, right? So you see, it's interesting to know that we have different options. We can work from the beginning or work from the end, okay? But for now, we will start with work from the beginning way, like we choose the earliest activity first, okay? All right. So now we are almost there to come up with a solution, with a strategy at least, okay? So actually our intuition tells us that we should choose an activity that leaves as much resource as possible, right? Our intuition tells us that if we choose A1 and then there is 12 hours left, or we choose A2, but there's 11 hours left, then our intuition is that, okay, I will prefer to choose A1 because we have more resource left. And more resource left means that we can probably schedule more activities, right? Although we are not sure, it's just a likelihood, it's just a possibility. It's more probable that because we have more resources left, okay? So why not we just stick with this intuition? And whenever we can choose among activities, we can use this intuition to guide us. We can choose the activity that has the earliest finish time, okay? So that's because it has the earliest finish time, then it will leave us as much resource, as much remaining time as possible. All right. Okay, so let's work on this example. Let's work on this example to complete the solution. Okay. So let's choose A1. Then what happened is that A1 is chosen among the remaining activities, right? There are some activities that cannot be chosen because they are not compatible with A1, okay? If you look at A2, it starts at 3 o'clock, but 3 o'clock is before 4 o'clock, is before A1 finished. So there's no way to schedule A2. And similarly, there's no way to schedule A3, A5, or A10 because they all have an overlap with A1, okay, onto the time scale, okay? So we can only choose among A4, 6, 7, 8, 9, and 11 among the remaining activities, okay? So when we choose among those remaining activities, we will use the same strategy. We still want to choose the one that has the earliest finish time, right? Because we want to save as much time as possible. So among the remaining 6 activities that are compatible with A1, actually A4 has the earliest finish time. So we can choose A4, right? So that is our second step of making a greedy choice, okay? And then after A4 is chosen, again, we need to remove some activities, right? We need to remove A6 and A7 because A6 and A7, they have an overlap with A4, okay? Since A4 is chosen, then obviously we cannot choose A6 or A7 anymore. All right, so there are A9, A8, A9, and A11 for now as the remaining activities. What we can do is that still we want to choose the one with the earliest finish time, which is A8 in this case. All right, so we choose A8, and now A8 overlap with A9, so A9 is also gone. So the remaining choice, the only one remain actually is A11, and it's, of course, it has the earliest finish time. Okay, so now we hit the boundary. If we hit the ending condition, okay. So we used up all the space that we have. Then the solution is A1, A4, A8, and A11. Okay, so quite straightforward, right? As long as we take this strategy, it's quite easy to get at least one solution, right? So although this strategy doesn't mean that, doesn't guarantee that we obtain all the possible solutions, but it is one solution, right? All right, let's look at how we can actually implement this solution. Okay, so this is an iterative implementation. Okay, so that means we have a recursive implementation as well. Anyway, let's look at this greedy activity selector, this procedure. Okay, so this procedure, it takes inputs the starting time and the finish time into arrays. Okay, and also it also assumes that all the inputs are already ordered by increasing finishing time. Okay, so this implicitly says that we need to sort all the activities first, which comes with some additional cost, some running time cost. So that's important to keep in mind with. All right, so this actually, what this algorithm does is to initialize a data structure, initialize a set, okay, which is the capital A, and all the chosen activities will be stored into this set A, okay? And after it ends, it will return this whole set when the procedure is done, okay? So let's look at the remaining code. And this second line of code actually simply initialize the sets with A1, okay? Because A1 must be chosen because it is the first activity, okay? And the K, actually, it's an index that indexes the most recent addition to the set A, okay? And the case elements in f of k, it's always the maximum finishing time of any activity in A because it's the most recently added element to the array F, to the set A. Okay, so if we look at line 4 to 7, it's a for loop, right? So it's a for loop that iterates from 2 to n, right? Which is the range of the remaining parts after A1 is selected, right? After A1 is selected, we need to iterate from 2 to n because we have n in total, okay? So within this for loop, there's an if condition, okay? It checks whether the starting time of activity I is greater than the finishing time of the activity K that is within this set A, okay? Because at the beginning K is 1, so at the beginning, so this Fk is just F1, okay, which is the finishing time of the first activity, okay? So if this condition is satisfied, which means the starting time of activity I is later than the finish time of activity K, which means as the activity I is a compatible one, right? Because it is compatible, we need to select it, okay? And that's also because all the activities are ordered by the increasing finishing time, okay? So the first one, the first compatible activity that we have encountered will be the one that we need because it will have the earliest finishing time, right? Based on this condition, because they are already sorted in terms of finishing time, okay? So if AI is compatible, then we will like basically use this union operation to incorporate AI into A. And we need to update K because now I is the index for the activity that is newly included, right? Newly selected. So the next one, when we are compare the new I with the Fk, so this Fk would be the previous I, right? Would be the previous activity that is just included into the result. And in this way, I think this procedure is very self-explanatory of the previous couple of slides that I showed to indicate the process of how to select activities. All right. So let's just to run through this again. Okay, use a concrete example, but this time because we have code now, we can keep an eye on what this what this set A is and what this index K is. At the beginning, we just choose A1 because it's the earliest. It's the earliest. It's the activity that has the earliest finishing time among all activities. All right, so we choose A1. We initialize capital A with A1, and the K is initialized to 1. So next, when we iterates I from 2 to n, right? So I will be first 2, okay? But now since A2, if we look at S2, so this is S2, right? The S2 is 3, which is not greater than the F1. So let me write F1 here. So the F1 is 4, right? So the S3 here is smaller than F1. So A2 will be incompatible, right? So next, we will have, oh, so it shouldn't be S2, but it should be S2, right? Not S3. There should be S2, and this 0 would be S3, right? It's also smaller than F1. So until we have met A4, which is S4 here, S4 equals 5, which is greater than the F1 4 here. So A4 would be the one that we incorporate into the set A, and then we need to update the K to 4. So from the next iteration on, we need to compare the SIs with this F4, okay? Because we need to see which activities are compatible with this new finishing time boundary, finishing time condition. Okay, so of course A5 is not compatible, 6 is not compatible because we're comparing these with the F4, right? With the F4, and this is not compatible until we see the S8 here, S8, right? S8 is 8 o'clock, which is greater than F4. So that is a bingo here. We need to select A8 into the activity, into the set, okay? And then update the K to be 8. So now we will set this F8 to be the one that we are comparing with, all right? So until we have lastly incorporated the activity A11, then we have basically everything solved, right? That's pretty much very close to the strategy that we described at the beginning, right? All right, that's an one iterative implementation of the algorithm, actually. So can we have other heuristics? I mean, the current heuristics that we use is the one that has the earliest finishing time, right? So what about, instead of choosing the activity with the earliest finish time, what about we choose the one with the latest start time, right? That is also a different way of thinking, right? It's a kind of backward, right? We will start from the one with the latest start time, right? Say it's just a backward thinking. We select A11, right? And after A11 is selected, we will, similar to the forward thinking, right? We will have a changed space of selection, right? Because A11 is chosen, then we can only consider those that finishes before the A11 starts, which is 12 o'clock. Then we need to only consider the space before 12 o'clock, right? We need to consider those activities that finish before 12 o'clock, right? It's just the other way around of solution. Then I use 12 o'clock as a threshold. We need to choose the one that has the latest start time, which is A9, right? Because A9 has 8 o'clock as start time, and that is the first one we came across. So A9 would be selected, and the A9 is selected. We will have the remaining parts. Among the remaining activities, we can choose A4, right? And A4 is chosen, and A2 is also chosen. Then we will have A2, A4, A9, A11 as a way to as just one solution to the problem. So so far it's so good, right? It looks close. It looks correct, right? Because it's also scheduled 4 activities for us, actually. But this this way of thinking in this condition, in this particular example, it's not totally correct because we didn't look at the conditions yet. Okay, the condition is that all the activities are sorted by this finishing time. Okay, so the activities, they are ordered like by the finishing time from 4, 5, 6, 7, 9, 10, right? So that is an order of the activities. If we use the latest start time as our heuristic, then it actually doesn't work with this sorted time with finishing time, the sorted activity with finishing time. We actually need to sort them regarding the starting time. Okay, so for example, let's look at this problem. If we sort the activities in increasing order of the start time, right, then the activities would be in a different order. Now, A3 would be the one that starts first, not A1, okay, because A3 has a 0 o'clock starting time. Then it will be A1, and then A10, right, because A10 starts really early, okay? So assume that we sort all the activities in such an order of increasing start time. Then we first choose the last activity, right? Which is 11, right? Let me clean up. So we need to choose A11 first, right? And then we need to choose the activity with the latest start time among the compatible activities, which would be A8, right? A8 and A4, right? And A2, right? That is A2, A4, A8, A11, okay? So, so this heuristic, this second example, it actually doesn't differ too much from this previous slide. We also have a 4 actives selected. So what if we choose the, what if we use the heuristic that we select the latest start time within the second example here, after we have sorted all the activities in the increasing order? Okay. Oh, okay, that's exactly what we did. Okay, all right, I made a mistake. So we actually chose A11 and A4, A8, A4, and A2. Yeah, that's correct. So what I mean is that this way of choosing the latest start time is only correct if we have sorted all the activities with the increasing order of starting time. Okay, it doesn't necessarily work if we start, if we choose the one that had, if we sort all the activities that with the increasing finishing time. Okay, so yeah, I should write a counter example that's showing that if we sort the activities by increasing finishing time, then this heuristic would not work. Okay, but I didn't have this slide here. Okay, so I'll look into this. So probably I can provide a counter example next time. Okay. Anyway, let's go to the next slide for further analyzing the algorithms. There are different ways just by reference. It doesn't seem like these different implementations would affect the running time of the algorithm. Yeah. So I spoke of running time. This algorithm is quite efficient actually, because It's just an iterative search over all the kind of a linear search over all the possible activities, right? But the correctness is not needs to be examined carefully in terms of how the activities are sorted in order. Okay, so it's actually quite straightforward, right? Because we use one for loop to iterate over basically almost all activities from 2 to n, right? And it's more or less, it's just like big theta of n, right? But actually, we didn't consider the fact that we sort all the activities just before we run the greedy greedy activity selector. Okay, so strictly speaking, we need to say that it's at least n times logarithm of n. Okay. Yeah, but somehow if we are able to sort the problems like with some more efficient sorting algorithms like the linear time sorting algorithms, because so far the examples we have all have starting time as integer numbers, and for integer numbers it's actually we are able to apply some efficient algorithms to sort all the numbers. All right. Okay, so that's the implementation for well, the iterative implementation for the activity selection problem. So if we try to connect this problem with dynamic programming, it's actually doable. So let's look at the optimal substructure here. So it's a little abstract now. We use mathematical notations, okay? We use the capital S with subscripts from I to J to indicate the set of activities that starts after AI finish and finish before AJ starts. Well, it's actually, this Sij is defining some range, right? It's defining an interval or a range that starts after AI finish and before AJ starts, okay? So it's a range, and we wish to find a maximum subset of mutually compatible activities within this range, okay? So this capital S is a range, and we want to find a maximum subsets of activities that we indicate as Aij, okay? So this Aij is a set of activities that is within the range of Sij, but we want to maximize the size of this Aij, okay? And let's consider this problem. So let's assume that AK is within this solution, is within the optimal solution, okay? So actually, we are left with two sub-problems. You know, just like the way we split, we divide the problem for the matrix chain multiplication, right? So we need to basically consider two ranges. One is to the left of K, and the other is to the right of K. Okay, assume that AK is already in the solution. Then we need to find, we need to first look at the left range, which is start after AI finish, but finish before AK starts. Okay, we need to do this Sij is the left range, and this Skj is the right range, which is to start after AK finish. Okay, so let's indicate the solutions to these two ranges as Aik and Akj. Right? Given AK, we have split the original problem into two segments, into two sub-problems. All right, so it's just such a relationship we can extract easily, right? So the original problem is the composition of the left sub-problem plus the activity in the middle, okay? So AK is in the middle, and then plus the sub-problem the right subproblem from K to J. Okay, so if we, because A's, all the capital A's, they are sets. So when we describe the size of the sets, they are in such a relationship. We need to plus one. This one is for this single element set AK. Okay, so it's actually a very obvious optimal substructure. Okay, let's say now we are defining some magical functions again, right? That's a typical way of how to come up with a solution for dynamic programming algorithms. We use this solution to indicate a magical function to find the solution between the range of 0 and 16, right? We use this to indicate the original solution. So when we assume that we select A4, so this is a random selection, okay? On this slide, it's just a random selection. So if we select A4 into the final optimal solution, then we need to solve the left subproblem, which is from 0 to 5, which is to the left of A4, and the right subproblem, which is from 7 to 16, right? Which is to the right of the range. Okay, so this is a typical optimal substructure, right? So we are considering two ranges. After A4 is selected, there's two regions we need to consider, okay? Because there's space to make further selections on both sides, right? In this case, we are lucky to get another optimal solution, which is A1, A4, A8, and A11, right? So this is an optimal solution, okay? But what if we select A5 as the central activity? Then to the right we have from 9 to 16, and to the left we have from 0 to 3. That's also two regions to select, okay? But this time we are not lucky because A5 is too wide and it cancels out a lot of space. So if we choose A5 first, then there's actually only one compatible activity left, which is A11, right? So in this case, the solution becomes A5 and A11, which is obviously not an optimal solution, okay? So how do we list, how do we get all the optimal solutions? We need to basically iterate over all possible subproblems, right? Because choosing A4 is different from choosing A5 first. So we need to look at how our initial selection gonna affect the remaining parts, right? So we simply need to iterate over all possible AKs. So AK would be the one we first select, right? We need to iterate over all possible Ks. The solution would be AK, the union between AK and the solution to the left and the solution to the right. So this is a very typical dynamic programming thinking, right? And the recurrence would be like this, right? We need to use the size of the left subproblem to the plus the solution to the right subproblem plus 1, right? That will be the solution to the original problem AJ. Okay, so if we're gonna solve this, use dynamic programming, we're gonna replace this AJ with some 2D arrays, right? We use AJ as the indices for an element in the 2D array. So we can replace those notations with this C of IJ, C of IK, C of KJ plus 1, and so on, okay? So it's actually a typical dynamic programming. But this is good. Well, I mean, this is correct, right? But this is not necessary. This is an overkill. Because the special nature of this problem, we don't actually look into all possible subproblems. And we just use a simple heuristic would be sufficient to solve the problem, okay? So, I mean, as to the question of how do we decide whether dynamic programming is an overkill or not. I mean, it's a difficult question. I mean, basically, excuse me, how we decide is a very empirical process. Like we need to know the problem well. We need to know the excuse me. We need to know the nature of the problem. Like in the case of activity selection, the simple heuristics, like we must select the problem that has the earliest finishing time or latest starting time would be sufficient to solve the problem. Okay, really depends on the problem. All right, so I think today we can finish the rest part of activity selection, which is a recursive algorithm. Okay, because we first implemented a iterative algorithm. So this recursive algorithm, it's actually reflects some of the sets, the way of think of the activities as a set. Okay, so there's a union symbol, union operator used in this algorithm. Okay, so let's look at the procedure. And first of all, it takes some additional inputs, okay? Because it's a recursive algorithm, we need to use this additional parameter to indicate the whether it's an original problem or a subproblem, okay? So this K and N means that we want to find the maximum subset of compatible activities, which is the range of the subproblem, which is after AK finishes and before AN starts, right? That is how we define the range of the subproblem. Okay? And then we will let I be the K plus 1 because that will be the first one to start, right? And we will let AJ, we'll use a while loop to iterate I. So this I will only be incremented if the starting time is like the starting time of I is earlier than the finishing time. If the starting time of I is earlier than the finishing time, then we will skip that activity, right? We will skip that activity by increasing, by incrementing I by 1, okay? And then after the while loop is terminated, which means we find some activity S that has later finishing time than f of k. Then if that activity is still within the range, then we will put that activity into the results, right? And we will run a recursive call again onto the remainder parts, which is from I to N. Okay, because now I is selected. We will look at whether we will need to solve the remainder parts. Okay, so if that I is outside the range, then we simply return the empty, right? And that will be the boundary condition for this recursion, because when I is out of the range, then which means there's no activities can be selected in the remainder parts. So we can quickly look at how this algorithm runs. Because our initial condition is that in this case, we are solving the entire problem. So we need to let K to be 0, and we will let F0 to be 0, okay? And 11 would be the boundary condition. So we will call the recursive algorithm on between 0 and 11 as an initial call, okay? So look at the body of this recursive algorithm. We will let I be start from 1, right? And the I will keep increasing until it finds an activity that has later starting time than f of 0. Okay, so when A1 is selected, A1 would be the first will be the first activity being selected, right? So the next one we will call this recursive algorithm on from 1 to 11, right? Remember, within the body of the function, we will let the function call the recursive. We will make the recursive call between I and n, right? The next recursive call will start from I, right? So the next one would be from 1 to 11, right? So within this recursive call, we will have the same code executed, but I will start from 2, right? And we will keep increasing until we find a problem that has compatible, that is the first one that has compatible starting time, which is A4 here, okay? So the 4 will be the new condition, new starting condition for the recursive call, which is from 4 to 11, right? And then same thing need to be executed within this recursive call. A1, A8 will be selected, and then the last one would be from the last recursive call would be from A8 to 11. All right, and the last activity being selected is A11. So after the last recursive call is returned, actually within the body of this recursive call, there is one more recursive call that is on A11. That has argument SF11, 11, right? But that will return an empty set, right? The empty set will be returned, and then all the recursive calls will be returned, and the complete sets of A1, A4, A8, and A11 will be returned. Okay. Yeah, that is how the recursive algorithm is can be defined in this case. All right. I hope you have a good sense of what a recursive, an activity selection and problem can be solved by these greedy algorithms in this lecture. And on the next Thursday's class, we're going to talk about the Huffman code, which is another typical example of greedy algorithm, making greedy choices at each step of an algorithm. And also we'll talk about knapsack problem. So knapsack is a very classical example that connects with both dynamic programming, okay? And a variant of knapsack is actually only solvable with dynamic programming, while another variant can be solved with greedy algorithms. Okay, so yeah, that's pretty much for the lecture today. And there will be a quiz question. Okay, I will release a quiz question on Canvas. All right, thank you, everybody. I'm gonna stop the recording.